students. Uh, this short video is is to explain to you the concept of mean temperature of heat addition and how to find out mean temperature of heat addition in case of a power cycle, that's Rankine cycle. So please remember these things, and you are taught in the class that the capacity of the heat, given quantity of heat, to get converted into work depends on its quality. उष्णतेमध्ये फक्त क्वांटिटी महत्त्वाची नाही, तर क्वालिटीसुद्धा महत्त्वाची आहे जर तुम्हाला उष्णतेचं रूपांतर मेकॅनिकल एनर्जीमध्ये करायचं असेल तर. सो इफ यू वॉन्ट टू कन्वर्ट हीट इन टू मेकॅनिकल एनर्जी, you should know what is the quality of heat. What do you mean by quality of heat? The quality of heat is the temperature at which the heat is available for getting converted into mechanical energy, right, or work. That is called as quality. So that temperature, higher the temperature at which heat is available, higher will be its capacity to get transformed into work. And so high temperature of heat, or the temperature of heat, tells you the quality of heat. Higher the temperature, higher is the quality of heat, right? And this thing you can see from Carnot engine. Now see, let's look at the diagrams. So what you see on the screen are two diagrams. On the B diagram is of Carnot engine. So you know the Carnot cycle. So Carnot cycle operates between two temperatures, T1 and T2. So let's say from 1 to 2, the heat is added. I'll choose a different color. So 1 to 2, this is heat addition. Let's say Q1. 2 to 3 is work output, right? Work. And 3 to 4, heat rejection. That is Q2. And again, the working substance is taken back to state 1. The work is input here. Okay. But efficiency of this Carnot engine, and you know the Carnot engine, all the heat, the processes are reversible, right? 1 to 2, 2 to 3, and 3 to 4. Please note that the heat addition is at constant temperature. And you know that the efficiency of Carnot engine is given by, of course it is given by Q1 minus Q2 by Q1, but this is also T1 minus T2 by T1, right? This is the efficiency of the Carnot engine. And you can see, if you want to increase the efficiency of Carnot engine, you would like to increase the temperature. If the temperature is higher, the efficiency is higher. Now you can say, you can also lower the temperature of T2, because the numerator then will increase, and then also you'll get higher efficiency. But there will be limit to decreasing the temperature of sink, the temperature of the surrounding. You can't lower, but you can choose the fuel which gives heat at higher and higher temperature. So T1, if T1 is high, then the efficiency is higher, right? Now this is the principle which we would like to use in case of Rankine cycle, and that leads to the concept of mean temperature of heat addition. So what you have understood is quality of heat is important, and quality of heat is indicated by the temperature at which heat is available. Now let's turn to Rankine cycle. So in the Rankine cycle, let's say this is the Rankine cycle. See, I'm drawing on a iPad which has smooth surface, so that my lines are not really straight, or even the curves, they are not really smooth. So please bear with that. So let's say let's start from some point. Let's say start from, generally we'll start with turbine. So the steam, let's say steam has already entered the turbine, and I'll start from there. So this is point 1, and this is the work output. 1 to 2 expansion, and I'm writing it as 2S because it's a constant entropy. I'm drawing ideal Rankine cycle. Entropy at 1 and point 2S is same, so I'm saying 2S. Then this is 3, right, where the heat is rejected. 2 to 3, heat is rejected. 3 to 4, there is pump work. We can say saturated liquid is pumped. And from 4 to 1, right, 4 to 1, this is the heat addition. Okay, 4 to 1 is the heat addition. Now see, we are interested in, we just said that higher the temperature at which heat is added, higher is the efficiency, or more of the heat will be converted into work. But now here you can see that the heat addition here is from 4 to some point. Let's say I can write some point here, P is saturated liquid. The heat addition is not taking place at constant temperature. The temperature is varying from P, again let's say Q, that is the temperature is constant, and from Q to 1 the temperature is changing. So you can see that heat addition in Rankine cycle is not taking place at constant temperature as it takes place in case of this Carnot engine. Okay, but the thing is, we would like the heat transfer to take place at higher and higher temperature. Okay, so now in this case, in the Rankine cycle, if you want to find what is the heat supplied, the heat supplied is area under the curve 4 to 1, right? All the heat supplied can be found from to find out this is the area. I can say 4 to 1. So this entire area is the heat supplied from 4 to 1, whatever, that is the heat supplied. Now this, we want to find out the quality of this heat. Now how do you find out the quality of it? Then you have to find out at what temperature heat is added. But you know that here the temperature is changing, so it's not a constant. So we should find out the average temperature at which heat is added. Okay, so if you want to find out average temperature at which heat is added, what we will do is, we will imagine as if we will imagine that the heat is added at constant temperature, but the same amount of heat is added. You know, we just found out the area under the curve 4 to 1. So the area under the curve, it represents heat transfer, heat supplied. The same amount of heat is added at constant temperature. How would you represent it on the diagram? That will be imaginary thing, but we can say that suppose this 3 to 4, we said it is pump work where liquid is pumped. Now we will say that we want to add the heat at constant temperature, so we will take it further up. Okay, let's say we are taking it further up to 0.5, and from 5 we add the heat. Okay, we add the heat. Okay, now we say that this area from this 5 to, we can say 6. Okay, now this is an imaginary thing. 5 to 6 is a constant temperature heat addition, but we can say, suppose we say that this area under 5 to 6 is this, because we are adding this area. Please note, this area was not there in earlier diagram. So this triangle is the additional heat area. Even, yeah, so we can say that because of this, the 5 to 6, all the heat that is added is given by this area. And this area and the earlier area, if they are same, then we can say that the same amount of heat is added, but it is added at constant temperature, right? So that temperature is T min, average temperature. So what we have done is, we are replacing the line chart 4P1, 4, please note 4P and 1 by a line 5 to 6. In both the cases, total quantity of heat added is same. Okay, now in the diagram it may not be very clear, but you have to, the principle is that heat added from 5 to 6 and 4 to 1 is same. And then we will find out now, if heat added is same, then we will find out what is this Tm, what is the constant temperature at which heat is added. Now how would you find it out? Let's first find out what is the heat added from 4 to 1, right? From this is the line 4 to 1, right? What is the heat added? How would you find it out? You will find it out, let's say it is Q1, and you will find it out as H1 minus H4, enthalpy at 0.1 minus enthalpy at 0.4, right? So at 1 it is about to enter the steam turbine, at 4 it is about, at 0.4 it is about to enter the boiler. So H1 minus H4. And now we are saying that if this heat addition, if hypothetically, not in a real sense but imaginary process, it is taking place between 5 to 6, then we will say this heat transfer, same amount of heat transfer is there. Now you find out the area under this curve. Let me make another 5 to 6, right? This is the 5 to 6 green color, and this area, so that is the same amount of heat. So we can say That's a rectangle. Please note, this is phi 6 and this is entire thing is rectangle. So area of a rectangle is height into its width. So this will be equal to Tm is the height, that's the mean temperature of heat addition, into 6, it's moving from 5 to 6, and x-axis is entropy, right? So what is the width of this? Height of this rectangle is Tm, width is S6 minus S5, right? S6 minus S5, change in entropy because of heat, right? So this is the equation which you are going to, this is the equation you get, and from this you can find out the mean temperature of heat addition. This mean temperature of heat addition then is H1 minus H4 upon S6 minus S5, right? So if you want to find out mean temperature of heat addition, you have to find out the total heat added by considering the temperature at which the steam is about to enter the boiler. The temperature at which you find out point 1, what is the enthalpy of at point 1 at which the steam is about to enter the boiler. This is point 4 at which the water is about to enter the boiler. Here steam, I said point 1, steam is about to enter the turbine, I'm so sorry, and at point 4 the water is about to enter the boiler, right? So find out these enthalpies. H1 minus H4 is the heat transfer, upon find out the entropy at point 1 and entropy at point here. Please note that you can see that S1 these are 3, 4 and 5 are constant entropy, they are on vertical lines. So I can write this as in order to be more clear, this will be H1 minus H4 upon instead of so we can write this is H6 minus H5, so I can write this also as S1 minus S4, right? S1 minus S4. Please note 1 and 6 are on the vertical line, so entropy is same. 3, 4, 5 are on vertical line, so I am just replacing 6 by 1 and 5 6 by 1 and 5 by 4, right? So basically in a Rankine cycle you will find out enthalpy change when water is heated to superheated steam or whatever is the final condition when it enters the turbine. Find out the enthalpy change, divide by the entropy change, and that will give you the mean temperature of heat addition. Why Tm, mean temperature of heat addition, is important? Because that is going to tell you how much of the heat supplied is going to be converted into work, and that you get from the Carnot engine. So if you see here, if this is your now consider we have converted the Rankine cycle into a Carnot engine. Please note, now here it is 5, 6, 2s and 3. This is the Rankine cycle, and so mean temperature of heat addition is Tm. So that efficiency is Tm, right, minus, let's say if this is the temperature T2, you can say T2 by Tm. This is, so basically we are drawn an equivalent diagram of a Rankine cycle, equivalent in the form of Carnot cycle. So you can see that efficiency is Tm minus T2 by Tm, and Tm is mean temperature of heat addition, and that is higher the mean temperature of heat addition, higher will be the efficiency of this Rankine cycle. Thank you.